Okay, I'm going to share with you a problem that I found interesting that was made aware to me about 2.5 years ago by Gary Antonik. And it has to do with colliding masses producing some digits of pi. In the diagram here, imagine that this is a horizontal surface with a 1 gram mass sitting here, a wall there, and a mass of m grams coming in from the right. I think you could imagine if the mass of m grams was also 1 gram, that these two would collide. The initially stationary mass would hit the wall, bounce off it, and come back and hit the other unit mass and drive it out to the right, and there would be no more interaction. If we counted the number of bounces when that happens, we'd get to 3. 1 on the wall and 2 of them between the two masses. Now let's ask what happens if we make this mass coming in much larger, say 100. If it were 100 grams, the 100 gram mass would come in, it would hit the 1 gram mass, and that 1 gram mass would rattle back and forth between the wall and the incoming 100 gram mass. Eventually it would drive the 100 gram mass out, and eventually there'd be no more interaction. If we do the Newtonian physics exactly, with an ideal situation, which physicists love to do, make things frictionless and energy conserving, if we do that and count the bounces, for the 100 gram mass, we get 31 bounces. Now, I've done the mathematics for the case where we successively increase the ratio of the masses by a factor of 100. And I've made up a little table here that reports the results of that. Now, people are finding this amusing, aren't they? If it's 1, it was 3 bounces, then 31, then 314, and so on. And most of you will recognize those as the digits of pi. Now, isn't that interesting? And of more interest is, does this continue, this pattern? Maybe forever. So let's see what happens when we analyze a little more. The Newtonian physics can be solved exactly, and we can write down the velocities of the small mass and the large mass after an odd number of interactions. And those equations down at the bottom show what those velocities are, and you can use them to determine just how many bounces you're going to get. So it's all analytic, all idealized Newtonian physics. When you do that, you've reached the following conclusion. If the mass ratio is 10 to the 2n, then you're going to reproduce the digits, n digits of pi, if the last half of those digits are not 9s, nearly half. Now, pi is known to a lot of places now. And as of a month ago, it was about 10 trillion places. But just recently, someone announced on Pi Day that they figured out pi to 8 quadrillion digits. And so, since there aren't such sets of 9s, we can be pretty sure that almost 16 quadrillion digits of pi can be produced in this ideal system. So that's kind of interesting. And as pi gets known longer, the chances of the last half all being 9s we can think of as quite small. Now, if such a set of 9s were there, you'd get 1 more bounce. So that's worth noting. And also of interest, this will apply to other bases as well. You multiply by the square of the base and you produce the digits of pi in that base. There are some bases that do have enough 9s, typically for very short numbers of digits, where you get 1 more bounce. And then finally, in the real world, Newtonian physics doesn't apply. Relativistic physics applies as far as we know. And if we solve the relativistic problem, the number of bounces is not independent of the velocity of the incoming mass. It is independent of how far the mass is from the wall, but it depends on the velocity. So I've taken a specific case where the incoming mass is coming in at 30 meters a second, which is about what you drive on the highway. And look what we get now with the number of bounces for relativistic treatment. And so relativity spoils the show. And thank you for your attention.